Okay, so multiplying vectors by scalars. Now, a scalar itself is just a number. It's not a vector. And when we multiply a vector by a scalar, we're increasing the magnitude of the vector. Okay. The direction of the vector, there's no influence on it. It's actually parallel. And a lot of times they'll call scalar vectors collinear. In other words, they go in the same. That's not very good. That looks a little more parallel to the original. They just have different magnitudes of each other. So, for instance, let's make that a clone. This is our vector A. Okay. If I were to take vector A and add it to vector A again, I essentially have vector A and vector A, right? Or you could see this as 2 vector A, okay? This vector, 2 vector A, can be drawn, and I'm going to do my best here to keep it parallel. I think it's got like a slope of 2, so I think it should be like that. Hopefully there. This 2A is a scalar multiple of A, okay? In other words, it's twice the force, twice the magnitude of our original vector A. Okay, that's all it is. If we were to multiply by a negative scalar, say I decided, I would like to see -3 vector B. Okay, well here we have our vector B. And because I can't just flip these around, what I'm going to do, whoops, I'll move it over a little. So I'm going to take 3 of these, and hopefully they fit on the page. I'm going to take 3 of them. So 1, 2, as best as I can, and 3. And all I'm going to do is I'm going to change the direction of them, right? Well, we talked about a negative vector. In this case, it's still parallel, but it's just going the opposite direction. So this vector is technically 3 times the magnitude of vector B, but going in an opposite direction. Just like we talked about when we're subtracting and adding vectors, we're just changing direction if it's negative, okay? So to go along with that, let's say we're building resultant vectors. And we want the resultant vector to be a scalar multiple of our original vector. So let's take, I guess I'll take vectors A and B again, since I already have them. Here's my A, here's my B, we'll bring them down so we have some room. Okay, let's say we're going to add these two together. So I take, there you go. We take our vector A, and we're going to add vector B to it. That means our resultant vector, and I should write these in to make sure we got our stuff. Here's A, here's B. Okay. A resultant vector, we'll do in red, when we add the two together, is right here. In other words, this is vector A plus B. So new resultant vector. Well, let's say I need the scalar multiple of that. I need vector 2A plus B. Okay. Well, there are kind of 2 ways we can go about it. We're going to use this vector to prove it. What I'm going to do is I'm going to copy this one, clone it. There we go, perfect. And I'm going to clone it again. Clone, there it is. So assuming everything works out, this would be essentially the magnitude twice as large as our original AB. Essentially, I took 2 of them and put them tail to tip each, and that's twice as long. Because of distributive property, what this states, distributive property being that I should be able to distribute my 2 in, this should be also the equivalent of vector 2A plus vector 2B. So I should be able to take scalar multiples of my original 2 and do the exact same thing. So let's do that. We'll clone 1. Okay, so here's my vector A, and we'll clone it again. 2. So here's a scalar multiple of 2. I built it twice as large. So this is now 2 vector A. And remember, this is 2A plus B. And I should be able to take 2 of vector B, clone, and clone again. Hopefully I did this properly. And we end up, oh, can I move it closer? Not quite there. I guess I've missed something a little.
to be exact as possible in order for this process to work out. This guy's got to move. Well, this is your resultant vector, and I guess I've made a small error in my putting the vectors together. But what essentially this is that this is now vector 2b, and the resultant vector of these two is the equivalent of finding a scalar multiple of the original resultant vector. I know I'm off by a little here. That's because of my human error. Okay, mathematically, this works out due to distributive property. The last major concept that they probably want you to work with is, let's say we had to find a scalar multiple of an already scalar multiple. So let's say they want us to find 3 of maybe vector 2a. Okay. Well, according to associative property, that's the multiplication rule, because this is technically multiplying a scalar times a vector, this is, you could think of it like being multiplied together. Well, the associative property, what that means is you can multiply things in any order you like. Okay. In other words, I can multiply the 3 times 2 first if I wanted, and that would essentially give me a 6 of vector A. Okay. So, and this is going to be a hard one. I'm going to try my best to show it to you here. Let's take our vector A one more time. Oops. I'll clone it as best I can. Clone and bring it down. So, we need 3 of vector 2a. So I'm going to build a vector 2a here. Here's one of them. Make this an infinite corner. Okay. There's 2. So here's now my vector 2a. I know it's probably a little off because the tips aren't perfect. But I've now built vector 2a. And here it says we need a multiple or 3 of these in this case. So I'm going to group these. Oh, I actually have to make this a little clearer. It's a lot of work to this silly stuff here. Can I get them? I'm going to move. Sorry. I should pause for this part. Okay, let's put these together. Group and infinite corner. Okay, good. So this is now my 2a again. And it says I need 3 of these. So if I take it, 1, here's 2, and here's 3. Well, this same idea says that this should be the equivalent of a scalar of 6a. And instead of me pulling out 6 of these vectors a, would you want me to do that? You want me to pull it out so you can see it? This is essentially the idea. If we count, because we use originals, we have 1, 2, 3, 4, 5, 6. And that's essentially that. What it is we can multiply the scalars by themselves first. We could do the opposite order. We could have 2 pairs of 3a. If I kind of break it into a purple here, I want you to think of this being a vector in itself. This would have been a scalar multiple of 3a, and we actually have 2 versions of it, 3a. So again, associative property, I could have gone a scalar multiple of 3a, and I need 2 of those, or I need 3 scalar multiples of 2a. And either way, all the same thing essentially equal 6a. Okay?